we'll try to get used to this new hybrid world. So firstly, seminar structure. There's the website. So these seminars will be every Thursday, 3 to 5 during the semester. The first 6 weeks, we will cover fundamentals. So the lectures will be by Joel, Georg, and myself. And then in the second 6 weeks, we will invite expert working mathematicians who have done something with machine learning to come and talk to us. And tomorrow will be the first tutorial. So this is Fridays from 3 to 4 p.m. It is being recorded. Should we, is it, pause, stop recording, so it's recording, yeah. So it's being, yeah, so all lectures will be recorded and posted on the website. All lecture notes will be posted on the website. We'll have tutorials from 3 to 4. These are entirely optional, where we will give you a chance to play with training a model and experiment with what works and what doesn't work, which I think is extremely important to getting to know the subject. So all you need is a laptop, a browser, and a little bit of Python knowledge. And I think that's all for the... Oh, so the other thing that I wanted to say is that you can very much follow this seminar at 2 levels. You can come along to the lectures and get an idea of what machine learning is and what potential applications might be for a mathematician, or you can kind of go the more in-depth route, which is coming to tutorials, mucking around with models. And we really, you know, this is a totally optional seminar. We don't mind at all how you approach the seminar. So that's the seminar structure. Seminar principles. So we welcome questions, remarks, explanations. So we're preparing 90-minute talks. So if someone wants to interrupt, they're welcome to. If you want to ask a question, just ask a question. As Joel said, if you're on Zoom, please put it in the chat. We're learning together. I'm not an expert, and I don't think Joel or Georg would be claimed to be an expert either. What we are doing is trying to learn something together. So if I say something that sounds stupid, it probably is stupid, and you can explain to me why it's stupid. And also, examples are very important. So let me first just kind of give a personal hopes and dreams for machine learning and mathematics. So computers have long been used for exact computation. So a classic early example is the Bircham-Swinnerton-Dyack conjecture, which is one of the Millennium problems about ranks of elliptic curves, was discovered essentially by experimenting on a computer. And at that point, they were pushing the bounds of what a computer could actually do. So can we use them, i.e. computers, to suggest conjectures, relationships between fields? It's a very interesting question. And that was the subject of some ongoing work I've been doing with the AI lab DeepMind, which is basically using machine learning as a tool to see unexpected relationships. And the second possibility is machine learning might become a bicycle for the mind. So this is a term which Joel told me about, which is apparently a term that Steve Jobs coined when he first saw the spreadsheet. It's like, spreadsheets are quite a simple thing, but once you have it, you can play with a whole lot of things in a very experimental and very powerful way. And reinforcement learning in this work of Wagner that we have on the website appears to give a very powerful way that you can look for counterexamples in graph theory. The other thing that fascinates me is I think that mathematics, you can kind of turn this around. So the first 2 points are about mathematics using machine learning, but I also think machine learning can use mathematics. If you want an extremely pure, interesting, difficult data set, there's millions of them that are produced very easily using some mathematical function, for example. So there's this beautiful book, I'm not sure if you're aware of it, by Yuri Manin called Mathematics as Metaphor, where he uses mathematics to kind of explore humanity. It's I think it's a really beautiful book. And so if you think about machine learning as being this big nefarious thing, it's very interesting to use mathematics to kind of explore machine learning. Okay, so let's get started. So a learning problem is basically, you can think about learning in the sense that we understand it as a human. So when you're learning, you can get varying degrees of feedback. So you might be doing maths exercises as a 7-year-old, and the teacher is over your shoulder, and the moment that you write down an answer, the teacher says yes or no. So here the kind of feedback is very direct. Or you might be playing a game of chess where the feedback is much less direct. You make various moves, you have some sense that maybe things are going poorly, and then things turn on their head, and then you win. So here the feedback signal is much less. Okay? And in long mathematical arguments, for example, this is a case where the feedback signal is not very direct. And there's unsupervised learning where the feedback signal is non-existent. So you might be, for example, in the park trying to decide which dog belongs to which owner. And you're just observing the dogs running around like crazy. Sometimes they run up to someone, and that might be the owner, it might not. And after observing these people, at no point does someone say your answer is correct. Okay? So if you imagine on this slide going from the top, so this is immediate feedback, supervised learning. Reinforcement learning is some feedback signal, but you have to, it's somewhat indirect, and unsupervised learning where there's basically no feedback signal. Another example of unsupervised learning is learning from a distribution. So you're just given samples of a distribution, you have to learn the distribution. And this is a kind of widely recognized trichotomy in machine learning. Basically, as you can probably guess, the more direct your feedback signal is, the easier the task is. So roughly speaking, supervised learning in very rough terms is easier than reinforcement learning, is easier than unsupervised learning. But that's also very rough. I should emphasize that machine learning often uses a mixture of techniques. So for example, the AlphaGo really mixed supervised learning with reinforcement learning. Today we'll focus on supervised learning, and there's always this kind of, for me, a kind of monster in the background, which is like engineering and computer science. Like, sometimes these are really difficult questions from a kind of point of view of computer science, and that's always intimidating to me. And basically, certainly with the work with DeepMind, I feel that if you're trying to solve a very difficult mathematics problem, you shouldn't mix it with a very difficult engineering problem. So basically, you want to kind of get your machine learning structures as clear as possible in your head and as simple as possible, and then you would try to attack the difficult math problem. Okay. So this whole lecture will be on supervised learning, and the next few lectures will be on supervised learning, and then we'll have some lectures on reinforcement learning. And also, this is really, the seminar is called Machine Learning for the Working Mathematician, but it's really focused on deep learning, which we'll get to in the second half of this lecture. So I just want to give you some idea of learning tasks. These are not mathematical tasks. These are the tasks that gave rise to machine learning. So a very simple example, which has been incredibly influential in the field, is just reading handwritten digits. Okay, so you can imagine, you know, when you used to write a letter, you would put the letters in little boxes, and you can imagine that someone had to read those letters. So at some point, someone had the idea, well, maybe we could have a little computer that reads the postcode or something like that. Okay? And so there's an enormous database called the MNIST database. It's a kind of classic in machine learning of 60,000 image answer pairs. Okay? And these are the examples of the kind of, so these are, I think they're 28 by 28 bit grayscale images. And then someone's decided painstakingly which number they represent. And a very important aspect of this data set is that it contains entries where there's, no matter how much you know about the problem, there's no clear answer. Okay, so this, I've tried to write down something that's kind of 50% between a 0 and a 9. Yeah? So you can't, there's no right answer here. Okay, it's a very important point. And it's funny when you look at these kind of image recognition tasks, because we feel that we're kind of infallible as humans. But then you start seeing these edge cases and you're like, oh, maybe it's a banana, but maybe it's an elephant, something like that. Yeah. And so what we're actually trying to learn is a probability distribution. So we've got a grayscale image, 28-bit by 28-bit grayscale image. So what we've got is a vector of 28 times 28. So it's a byte. So it's a byte of data for every pixel. So it's 0 to 255, 28 times 28 times. Okay, so it's just a big long vector. And what we have to do from this is predict a probability distribution on 0, 1, up to 9. Namely, what do we think that this digit is? So that's a kind of absolutely classic supervised learning task. Some other classical supervised learning tasks are classify images into dog, not dog. So there's a binary classifier, and often it's very useful to keep the idea of a binary classifier in mind, even if you're interested in a more interesting classification problem. That's really much simpler. What is this a photo of? So that's a classification problem, but potentially across like all nouns in the English language, for example. Where are the faces in a photo? So when you're using a smartphone or something, it's able to find the photos. There's some kind of machine learning going on there. Find the faces. So non-visual tasks, another classic is mark email as spam, not spam. Speech recognition is a massive one. And also, as we will see in the tutorials, many kind of big data problems in mathematics. I mean, any situation in which you can generate, 10,000 or 100,000 cases easily by computer. So a simple example might be, imagine you want to see if machine learning can learn the Euler characteristic of a graph. So it's very easy to generate 1 million random graphs on 100 vertices or something. And it's very easy to compute their Euler characteristic. And so you have this very interesting data set, and you can play around with it. And you can come up with 10 examples immediately. That's one of the things that I find so interesting about kind of mathematics. And it's also it's a data set totally without noise, which basically never occurs in the real world, as far as I understand. I don't have very much to do with the real world, I should mention. So the first important principle is that many supervised learning tasks are about, or can be imagined to be about, or can be dreamed to be about function learning. So what do I mean by that? So let's consider the dog, not dog classifier. So what we can imagine is that, so we have a whole lot of pairs of images, which are represented by points in R to the number of pixel space. And we have we would like to produce a value which is correlated with the probability of this image being of a dog or not a dog. Okay. So if you think about this, you have, so a typical image, like a good quality grayscale image on your computer will have about 10 million pixels or something. So what you have is some points in 10 million dimensional vector space. And what you want to do is find some function which sends all of the dog points to 1 and all of the not dog points to 0, for example. Or one way of rephrasing this question is you would like to find a function that takes very high values on dog images and very low values on non-dog images, and takes the value 0 when it's uncertain. Okay. So that's what I mean by many problems can be recast as function learning. And note that there's no God-given reason why such a D should exist. Okay, we know that there's certain points in space and they have certain values associated to them, but we don't know that there's some big function. So another nice thing to think about is if you think about like an image, so this is a particular space, a particular point in 10 million dimensional space. And if you just take a random point, this is not an image that will ever show up visually. So you have some kind of interesting submanifold inside 10 million dimensional space, which is the image, the submanifold of potential pictures. And I think that we'll get back to this topic in a few lectures' time, kind of manifold learning. So our task is to approximate this function given, say, 10,000 of its values. And I guess the important principle is just like maybe this function exists. It's a leap of faith to say that this function exists. And just a little thought exercise, interpret all examples in the previous slide as function learning. So another important principle.
Sorry, is it a decision process afterwards? Because now you've met something to R, but in the end you still want to get dog or non-dog as a decision.
So Martin just asked, is it a decision process at the end? And what happens is generally you train this function, and then your final decision is made, like if it's positive, then it's a dog. If it's negative, it's not a dog.
But is it predetermined or is it then updated?
So
and only if it's like 0.5 is my cutoff on all versus data you say wanna be meta or something like that.
Yeah, so you would fix your cutoff to be 0, and then you want to try to train this function. But like that important point that like, so yeah, I think, so what Martin's saying is a very important thing, is that the God-given training set is just, a 0-1 function. It's dog or not dog. But what we end up training is a real valued function, which in some sense, which is we're trying to correlate with a probability that it's a dog.
That's about the distribution.
Yeah. Exactly. Yeah. We're trying to learn a distribution given certain values of it.
There's a comment from Jordan.
Okay, Jordan made a comment. So Jordan says, is it really a leap of faith to imagine there's such a function? Doesn't my brain return a probability of dogness given an image? Yeah, so I totally agree. Yeah, so in kind of cognitive processes, yeah, there is very much evidence. There's neurological evidence that there is some function going on in your brain which does return a dogness value. Yeah, but in processes that don't come from cognition, we might not know that such a function exists. Yeah, so Jordan asked the question, and that this example is thanks to Jordan Ellenberg. So this is an example from number theory, and I just want to use it to illustrate an important principle. So in the second tutorial, we will study this function from number theory. So this is an incredibly important basic number theoretic function, which is called the Möbius function, which got 10 different definitions, but probably the most easy to digest is just, it's the parity of the number of prime factors if the prime factors are all distinct, and if there's a repeated root, it's 0. Okay, Möbius function. And what my instinct would be that I would like to learn a function mu from, let's say that our input we're recording in binary, and so our input is a particular 0-1 vector in R to the number of bits. Okay, we might decide that we want to learn this on 10-bit numbers or something like that, 10-bit binary numbers. And so my instinct would be to say what we want to do is learn a function to R. But in this particular case, given the fact that the Möbius function only takes 3 values, it's better to learn mu hat from R to the number of bits to -1, 0, 1. I.e., we want to learn a probability distribution. sorry, a probability distribution on -1, 0, and 1. And I don't know, like, I don't know if that's obvious for some people in the audience, but like when I started working on this stuff, I just always kind of thought I'd be in the first case. And this really does not, in many, many cases, just works not as well as the second case. Okay. And another important thing is that basically, like, constraining something to be a probability distribution is unnatural. And so what we actually learn is a function to three-dimensional reals, such that when we normalize it using something called a softmax function, which I'm sure we'll go into more detail on later, we get the probability distribution that we're after. So actually, we're training a function which should be very large on what we think it is and very negative on what we think it's not. Okay. So the two important principles that I intended to get across here are recast as function learning, and sometimes think about a regression problem as a classification problem. So my principal kind of gained essentially by osmosis from talking to people is that typically regression problems are much harder than classification problems. So regression problems means actually trying to correlate with the real value function. Okay, so linear learning, we want to learn some function given training data. So n is some enormous number, like 10 million or something, and we've got some reasonably small amount of training data, so 10,000 pairs of input vector, output number. So we can try to fit a linear function. So we're just searching for a functional on R to the n, so a linear function to R. And there's a very important thing that I'll say at this point and probably repeat, and it'll probably lead to confusion at least 10 times before we get used to it. But there's a very common tendency in the machine learning literature to conflate linear and affine linear. And I think that basically you've just got to get used to this, and we'll continue this fine tradition.
So, Geordie, I need to interrupt you. There's two questions in the chat from the previous slide.
Sure.
So the first question is the function to detect the prime numbers better to learn than trying to learn the most?
Okay, I think so. The first question, so just to repeat.
The first question is from
Shuhua. So Shuhua is asking, probably also the function to detect the prime numbers is also better than learning the Möbius function. That's a good question. Yes, but you can kind of see in the, so we have a tutorial on the Möbius function next week, and you can kind of see it learning low prime numbers. It's quite amusing. And yeah, it's a good question. We should just do this. Try to learn the function, which is an indicator function for the prime numbers. This would be really fun. In terms of formulating the Möbius function problem, why would the domain of the function be continuous products of the reals rather than discrete? The kind of brute force answer to that would be, well, that's where we can apply machine learning. And it kind of tends to work. And that's a little bit what I'm saying in the terms of this like recast problem as function learning. It's not an obvious step. And it's definitely not an obvious step here, but it seems to work and be interesting.
But we can still be putting in discrete. Like we're only putting in vectors with zeros or ones.
Yes.
Yeah.
So what do you mean?
No, I mean, it's like, you know, the domain is continuous, but all we're ever putting in is zeros and ones.
Yeah. Yeah, it's like, so what Joel is saying is that even though the domain is continuous, we're putting in like the points where we're sampling are incredibly special points in this big vector space, which looks a bit weird. Yeah.
So that's why you get this real data.
Yeah, probably. So Jordan says, let's find out the tutorial which is better. Yeah. So Joel put together a collab on the Möbius function, and it's already been very fun, and I'm sure we'll have a lot of fun. Not this. So basically, the tutorial tomorrow is just kind of getting used to Python, and we'll probably do the XOR function. I guess it's yet to be totally finished, this tutorial. And then next week, we'll do the Möbius function. So linear learning, so we're trying to learn a linear function. And keep in mind that linear often means affine linear. So basically, if you think about this in terms of linear learning, so a very, very basic and important task in machine learning is to separate one block of points from another block of points via a hyperplane. And if we allow an affine linear function, this is saying that we're allowing ourselves any hyperplane in space, not just one that goes through the origin. So we try to minimize the mean squared error. So mean squared error of is 1 over n. Okay, we try to minimize this over W and B. So over n plus 1 real numbers. And this, sorry, got the square exactly as I did in the notes. So this is just linear regression. Okay, so this is just, we're essentially doing like a line of best fit. And it's convex. And we can solve exactly, or for large n, by a gradient descent. So basically, linear learning is not a mysterious thing. Something that we probably learned in first or second year. It's just linear regression. Yeah? So the next step is so-called kernel methods, which I just find the idea extremely. Oh, sorry. There's one more slide on linear learning. So linear learning is much too simplistic for many learning tasks, of course. So I love this quote: classification of mathematical problems as linear and nonlinear is like classification of the universe as bananas and non-bananas. Okay? So basically, whenever your data can't be kind of split up by a hyperplane, there's no way you can learn with a linear function. So we can't learn the XOR function. This is a basic observation made by some very early machine learning researchers. And the data set on the right is something that is a reasonably common thing that shows up, but cannot be learnt by a linear method. Yeah, absolutely. Like, if we have a hyperplane going through the zeros, so at the point 1, it's got to take at one of the ones, it's got to take the value 1, and so on the other side, it's got to take the value -1. Yeah. That's absolutely impossible. So there's a question. How about standard deviation rather than RME? So I don't know how to answer that question. I don't know what RME is. Okay, so maybe we can leave that till the break or something. So kernel methods. So the following paradigm I find you know, it's probably obvious to people that work in this field, and but it just seems extremely beautiful to me. So we have Rn, and then we have our, so we're imagining that this is the function that we want to learn. And then we have some kind of, usually non-linear, feature map. To some big Rn, and then we have some linear so this is basically, so we tried to say that linear learning is very simple, converges, a unique solution, it's great, but it doesn't always work. And often you can get around the fact that it doesn't work by having some nonlinear map into some big space, and after that, you just do linear learning on that space. So in that example before of the data set that's concentrated around a single point, which might be 0, for example, we can add a nonlinear measurement of this data, which is distance from the origin. So we keep the 2 coordinates and we add this distance to the origin, and now it sits up on this beautiful cone, and now we can just linearly separate it. So that, as far as I can make out, is the kind of basis of the idea of kernel methods. And my understanding of kind of traditional machine learning, like in the, prior to deep learning, was that many tasks were solved by cooking up interesting, cooking up as a human, interesting feature maps. You're asking what could possibly be useful. Yep, Gus? So Gus just asked, what is the formal definition of learning? Sorry, an informal definition of learning is you have some task, for example, recognizing a dog in a picture or something like that. And what you would like to do is train something, some predictor, so that it generalizes in a reasonable way. To generalize it. So you want some, so it's machine learning, so you want some mechanistic process which then generalizes. So you've got your data set which you can train on. It's not enough to memorize all the values of the data set. You actually want to be able to say, in this unseen picture, that is a dog or that isn't a dog. Okay.
You want something like a machine which gives a mark every time it sees it.
Yeah, exactly. Yeah. Yeah. And you don't necessarily want it to be right all of the time, but if it's right a lot of the time, that's already. Yeah. And so basically, and then what we're studying is methods in which we can mechanize learning. And one of them is a kernel method where we have this nonlinear map. And then, so this is, we specify this in some way, and then we learn based on that, we learn a linear function based on that. So one can think of the feature space as being like anything relevant to the problem. So, if you go to the doctor and the doctor has not yet formed an opinion about you, he asks you a whole lot of basic invariants. Like he asks you, what's your blood pressure? Do you smoke, etc. And these are like, this is like a feature map. Like these issues of, these aspects of humans are useful in deciding something about them. Phi is also called the representation, and this idea of representation is absolutely fundamental to machine learning. So basically, so Hinton says, for example, that a thought is nothing but an activation pattern in the brain, i.e. it's a vector in some space. So a thought is a representation. An example, which I find kind of mind-blowing, is, so if you just search on Google for Python Data Science Handbook in-depth support vector machines, there's an example where they take pictures of Tony Blair and George Bush. Pictures. And then they take the first 150 PCA components. So they do principal component analysis on the matrix, on the pixel matrix of these photos. So this lands in R to the 150. And then they train a linear classifier to R. Okay. And this is incredibly good at telling apart Tony Blair and George Bush. To me, like I'm sure like some of you, this is obvious, and this is just, you know, the amazing thing of things that happen that you already learned in third year or something. Like you do like principal component analysis on your on the grayscale image. So you basically have some matrix of grayscale values. Yeah. And then you do PCA on that, get a vector in 150 dimensional space. And then there's just, it's crazy. So it's basically saying that like inside this 150 dimensional space, Tony Blair is on the left and Bush is on the right. Pretty bonkers, I think. I mean, maybe, yeah, it's bonkers to me. It's maybe not bonkers to people that do this stuff. Learning representations leads to deep learning. So the idea here, so I hope I've convinced you to some extent that this is an interesting paradigm. So the basic point is that kind of for many, many years, machine learning functioned not particularly well by having a whole lot of humans, for example, analyze like what are important aspects of human speech, or what are important aspects of images, or something like that, to get this feature map, this nonlinear feature map into a sort of big space, and then you do linear learning on this. Now you can ask, is it possible for me to learn the feature maps? And that's what leads to deep learning. That's one way of approaching deep learning. Okay, so that's meant to be the break. So maybe let's have a 10-minute break or so. Yeah, so what we'll discuss, so I think that what FXY is asking is basically what happens up here if I put a big square root over all of this. And the answer would be, it's still convex, it still converges, everything's still great. So this is an example of a loss function, and we'll discuss that in more detail later on. Okay, we are beginning again. Now we're going into deep learning. We're going deep. So deep neural networks. So I find this quote from Geoffrey Hinton, one of the founders of deep learning. And he has some very inspiring interviews on YouTube. And in one of them, I'm not exactly quoting him, but this is what I picked up, is that if we think about our interactions with the world, they're incredibly complicated. Our abilities in any situation are vastly different to someone's abilities on the other side of the world, or someone that has a different background or something. So, but the way that we learn might be subject to very simple principles. And I find that a kind of compelling and very inspiring idea. So I just want to describe, like, in very, very vague terms, what happens in the brain. So what is a neuron? So, you know, the vast majority of neurons in our brain have source other neurons. And so you have various electrical charges entering. And exactly how a neuron behaves is very complicated. But our understanding of neurons is firstly that nothing happens until a particular charge is reached. And then something complicated happens. Okay, so the neuron fires, and there's incredibly, incredible subtlety in terms of how it fires, and there's a big temporal aspect. But this basic picture that we have these input charges, these charges are added up, so it's just a linear addition of these charges, and then nothing happens until a certain threshold, and then something happens. So I find it fascinating that firstly, as far as a neuroscientist is concerned, a brain is an object of classical mechanics. So it's, basically you can say what's going to happen to a neuron based on what happens in previous neurons. So I'm not sure if you've read these books by Penrose around the theme of the Emperor's New Mind, but I was fascinated by them when I was sitting probably in this lecture hall in first year doing linear algebra and calculus, and I hated linear algebra and calculus, and I was fascinated by Penrose's The Emperor's New Mind, and I thought, oh wow, I've got quantum mechanics in my brain, and I find it amusing that probably like it's much more linear algebra and calculus that was going on in my brain, and I should have paid more attention to that. And the brain has something like 80 billion neurons. So, the possibility that our cognition might be an emergent phenomenon out of quite simple behaviors at a neuron level is kind of mind-blowing. And so then there was an attempt to imitate this with the perceptron. So we have certain charges going in, x1, x2, x3, and then something coming out. And what comes out is the maximum of some constant and lambda1 x1 plus lambda2 x2 plus lambda3 x3 plus a, remember that linear is affine linear for us. So if you think about this function, it's got a very fancy name. It's called a perceptron because I guess people wanted grant funding in 1954 or whatever. But it's a very simple thing. It's just we just have a linear function composed with a constant function. So we have some linear function, and then at some point there's a cutoff and it becomes constant. Okay. And then the idea is perhaps we can build an artificial neural net by putting all these perceptrons together. So this is what a vanilla neural net is. So I'm calling this a vanilla neural net. It's also called a fully connected no skip connections. So if it's kind of dangerous to think too much about like the brain in these things, but it's a very loose analogy with questions in neuroscience, etc. But if you imagine the brain, you have a whole lot of neurons connected, and they connect back to each other, and there's various connections, a long connection and stuff like this. So this is just saying that everything is just lined up, and there's just forward connections. So fully connected means that in every layer, every neuron is connected to every other one, and no skip connections means there's nothing going more than one layer. So, and each layer is R n I to R n I. So this is a linear, so affine linear map, and then a so-called ReLU, which is coordinate-wise max of 0 and. Thank you. Okay, so we take our vector, we apply an affine linear transformation to it, we get a whole bunch of coordinates, and then if they're negative, we set them to 0. That's simple. That's what every layer is. So, and this is called the nonlinearity. So my understanding of it is that in early neural nets, they chose rather complicated functions for this nonlinearity, like a sigmoid function or something like that. And then slowly they settled on this not differentiable function, but somehow things work much better with the ReLU, and it's just an incredibly flexible, simple framework. Yeah, so these are all extremely important words: nonlinearity, ReLU. Okay, so whenever you see ReLU, it's just coordinate-wise max of 0 in your number. Okay. So the nonlinearity, it's, you know, so I'm a representation theorist. And so if I see a diagram like this, I think, oh, these are all vector spaces and these are all linear maps. And I can choose bases so that everything is incredibly simple. Huh? But the nonlinearity depends on the choice of bases. Okay, so there's this positive orthant on which the ReLU is the identity. And that orthant essentially nails down the fixed basis up to scalars. So the nonlinearity depends on the choice of basis. So this destroys symmetry. And we have a massive increase in expressivity. Okay. So what I mean by that is that, you know, without these ReLUs, this composition would just be a linear map, so it'd just be a functional, and we'd be back in the setting of linear learning. But with this ReLU, you can approximate an enormous number of functions, and Joel will go into that next week on the expressivity of neural nets. And deep is just synonymous with 4 or 5 layers, like bigger than 5 layers or something. So I used to think that deep had some kind of spiritual meaning. And my understanding of the history of it is that people played around very early on, even I think like 50s and 60s, with networks of depth 1 or 2, and they didn't get very far. And there's just been this kind of revolution in the last 15 years, which is viewing, like increasing parameters enormously and viewing training as a kind of engineering challenge and doing it on GPUs and stuff like this. And it's another instance where there's no real, as far as I can make out, there's no real new idea in the breakthroughs that happened kind of around about 2010 with, for example, image classification. The ideas had been there for 30 or 40 years, but what changed was the architecture on which you can train. I just want to kind of give you my picture of this from a kind of, like, you know, I love linear algebra, even though I'm still very bad at it. And I kind of love the idea of polytopes and convex geometry and stuff like that. And if you look at what one of these functions is, so each one of these is a piecewise linear function. So composition of piecewise linear functions is a piecewise linear function. So what I should imagine is that if I just choose my affine linear maps somewhat randomly, what I'll get is my first vector space will be broken up via various hyperplanes into certain regions on which my function will be linear. And now I can imagine moving these functions in various ways. So I can change my linear function, and I can also change my regions. And this is what will happen as we do training. These regions start moving around and the function starts changing. So this is one way. I mean, if you think about just this on the real numbers, you can imagine like a piecewise linear function, like just given by its graph, slowly moving around and trying to approximate what you want to approximate. So there's many views on deep learning, and we'll come to that in later talks. So I just want to go over the example of XOR again. So XOR was this thing that we couldn't learn with a linear function. And now if you just do a generic nonlinear map into R3, then these points won't lie on a hyperplane anymore. So you'll have four points, and they'll be the vertices of a simplex, of a 3-simplex. And so of course I can like trade a function which is 1 on one edge and 0 on the opposite edge. Okay. So this is an example of how kernel methods would solve the XOR problem. And here's just a neural net computing XOR. Okay. It's a simple example, but you basically can't do any, as far as I can make out, you can't really do any examples with neural nets by hand, and this is one that you can, and so that's why I'm just giving you this example. So we start off with these dots. So these are the points 0, 0, 1, 0, 0, 1, and 1, 1. I'm trying to learn the XOR function. So it should give you the value 1 when they're distinct and 0 when they're the same. Is that the question? Yeah, sorry. Yeah, I did ask like what function are we trying to learn? We're trying to learn, yeah, so it basically green means the value 0 and red means the value 1. Can you repeat the question? Can we always choose appropriate basis or more neurons to remove the nonlinearity? I can give a stupid example to this question, which is like, imagine that we have a point cloud and one of the points is 1 and one of the points is 0. Like we want to learn the function that's 0, one of them, one on the other. If we just put this into a high enough vector space, all of these points will be linearly independent and their vertices will span a simplex, a massive high dimensional simplex. So I can definitely find a function which is 0 on, like after applying this incredible, crazy nonlinear map into massive dimensional space. But the question is that meaningful? Like, you know, in Gus's question, like if I give you another point there that the training hasn't seen, will it still give me a meaningful answer? So the answer, like the direct answer to the question that was just in the chat is yes. We can always just increase dimensions to solve our problem. But the more important question is, would it be meaningful to do so? And that's much more subtle. You know, just to go over this example briefly. So here we add up the coordinates and we shift down by 1. So, you know, these points go to here, 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 and then we shift them down by 1. That's the first layer in our neural net. So that's the affine linear layer. And notice that at this point, we've just done a linear function. So there's no way we can separate yet. But now the nonlinearity comes to our rescue and shifts this point up to 0. Okay. And now I can find a function which is 0 and 0 here and 1 here, which provides my function. Yeah. And you can see here that you can imagine this space as being like kind of shifted around a little bit in a nonlinear way by the ReLU. So that there's the ReLU. And I think it's really interesting. It's much more difficult thought exercise to imagine actually training this example. So we'll discuss training now. And this is a lovely example to try to think about, try to visualize how training might look. So now, supervised deep learning. There's many solutions, and also a much better question is like, having trained this, is it meaningful on other data points, for example? So this is not meant to be a kind of example of learning. It's just an example of the increased expressivity of a neural net. And yeah, so maybe one thing that I forgot to say back here, sorry to shift between the slides. So this is a vanilla neural net. So this takes nothing about the problem into account. And in almost all of the significant applications of neural nets, for example, in image recognition or in speech recognition or something, the architecture of your neural net reflects the problem. Very important. So if you think about looking at an image, you don't, like initially, there's absolutely no interaction between something going on over here and something going on over here. You perceive edges, you know, you can kind of apply some metacognition and say you perceive edges and you start putting them together and then you start making a global judgment. And that's what a convolutional neural net does, which is what Joel will discuss next week. And then there's, for example, in neural nets that are meant to do speech recognition, train some kind of attention mechanism so that you have some kind of locality in time, but you've also got some pointer back in time where relevant parts of the sentence might come into play. So this is a vanilla neural net, which on almost all significant problems won't be effective. Okay? But it's the first example. So supervised deep learning. So we have data. So we have vectors in some big dimensional space. And then, for simplicity, we're assuming that we're trying to learn a real valued function. So this, as I've tried to emphasize before, this function may only be hypothesized to exist. So we choose a neural net architecture. So this is like a cookbook. How do you do supervised deep learning? And good cooks can follow this cookbook much better than I can. So we choose a neural net architecture. So you choose a depth and the intermediate dimensions. So this, in PyTorch or something, you'll plug these numbers in. And a rough heuristic, which I'll try to explain at the very end, is kind of surprising from a kind of traditional statistical point of view, is that the deeper and the bigger your neural net is, the better. So one way of thinking about this is that, as I say, I'm not an expert, but my impression of this is that if you have something that's expressed by like a very complicated neural net, you can ask it, can we shrink it? Can we make it smaller? But to go the other way is much more difficult. So now we've fixed our architecture. So at the moment, we're just choosing a vanilla neural net. So we split the data into train and test. So what that typically means is we'll make some pretty arbitrary choice of saying that 80% of this data, so we'll randomly select 80% of this data and say this is our training data, and then we'll keep 20% and we won't show that to the model, and we'll say that this is our test data. Okay. So it's extremely important during training to know basically whether you're overfitting. And you can do this by, so the test data, the neural net hasn't seen. And so if the success rate on the training and test data is roughly the same, then that's a good sign that your neural net is not overfitting. Okay. Overfitting would be, for example, just memorizing everything in the data set. So we do that split. Now we choose a loss function, we initialize, and then we optimize, and the result is a trained model. And there's a lot of subtlety in the choice of loss function, as far as I can make out. And optimization step is also somewhat interesting. And so that's what I'll handle on the next two slides. So yeah, so this is the next slide, but basically it's a choice of how well our model's doing. So we have a whole lot of, yeah, so once we have this net, you can imagine that we have, so this is our, what people often call the ground truth. So we can imagine, we can plug in a whole lot of values into our model and ask, how close is this to the ground truth? And the measurement of how close that is the loss function. It's the function we want to optimize during training. Well, yeah, it's the function we want to minimize during training. So choice of loss function. So we would like a measurement of how well our model is performing. So smaller values means better model. So we want to minimize the loss function. So standard choices. So for regression, i.e. predicting a real value. So we're trying to predict a function, and it really matters the value of the function, not just is it big or is it very, very positive or very negative, for example, in a classification problem. So the various choices like mean squared error, mean absolute error. And once you start getting into this stuff, basically in my experience with this, other people have essentially always trained the model that I was interested in. And so they had to deal with these issues. And my understanding as an outsider is that there's quite a lot of subtlety in the choice of these loss functions. So when we're predicting a probability, it's very good choice to use the so-called cross entropy. So if we're in a regime of a binary classification, what this looks like is, so each term looks like Okay, so what this is saying, so if you imagine the graph of, so imagine that for a particular value, our ground truth is telling us that it's 1. Now, if you look at the way that this function behaves, so it goes, so it's essentially the bit of log between 0 and 1, but minus that. So it goes down like this. Okay. So what this is saying is that if you're very sure that it's 0, so like if your model is saying it's 0 and it's actually 1, this cross entropy is enormous. Okay? And if you're indecisive, it's still pretty large. And so it's both encouraging you to make a decision. So like cross entropy does not like it when you predict everything with equal probability. It's wanting you to make a decision and it's wanting you to make the right decision, basically. So it's really punishing answers that are confident and wrong. Sam says, seems that G hat has some unstated assumptions about it. For example, a G hat which captures the training data exactly but is 0 everywhere else is definitely not the sort of function we are trying to learn. I guess we want to capture any problem-specific symmetries, either translation in the domain, have nice bounds and variation, maybe Lipschitz, etc. Can these sorts of assumptions be formalized? So this sounds like a discussion question. It doesn't sound like something that we can answer quickly. There's a discussion which I haven't yet really internalized about maximum likelihood, which Georg explained very nicely to me, which we will hope to discuss. So basically, this is an explanation of where these loss functions come out of. And also, there's an extremely important part of this, which is regularization, which is basically like adding, roughly speaking, adding some term onto your loss function, which encourages certain behavior or smooths out behavior. And it's a enormous subject. So a simple example of a regularization would be adding like absolute values of all your matrix entries, which would encourage your matrix entries to be 0 if they can be, for example. That would be an example of a regularization. So that might lead to a model that's much more, it's much clearer what's going on. It's much more interpretable. So, but we have this black box loss function. And the important thing to notice is that, so each of these parameters, it's just a matrix plus a bias. So the parameters here live in an n1 times n2 plus n2 dimensional space. So a matrix plus a vector in here, a bias. And then we have a similar vector space here, a similar vector space here, etc. So we just have a whole lot of, we just have an enormous vector space, and we have a loss function on this vector space. And you start at some point. So basically, you initialize and then do gradient descent. Okay. How do you initialize? Another big question. And my understanding is about 4 years ago, some French guy proposed this initialization scheme that just blew everyone away, and now everyone uses that. Yeah? So it's very much like it's still an evolving subject. So gradient descent is we update, so our new theta n plus 1 is theta n minus gamma times the derivative at theta n minus 1, the gradient at the point n of the loss function. Okay, so so it's like there's two different things going on here. There's the kind of point moving in the original space, and we're trying to learn this function. But now we kind of forget about that. The points are just fixed. We just have this big space of parameters of our model, and we want to learn, we want to optimize on that space. So we have this potentially very complicated function on a big real dimension, a big vector space, and we just do gradient descent. So we start somewhere, we compute the gradient, we go in the opposite direction, try to get smaller and smaller. And this is called so in traditional gradient descent, this is the step size. And in machine learning, this is often called the learning rate. Now, which is another thing that you have to decide on. And there's some heuristics for deciding, but. And usually you don't use gradient descent, but you use stochastic gradient descent, which just means it's the same formula, but we use a random small subset of training data. Okay, so if you think that your training data is probably like 100,000 training data or something, then when you compute this loss function, you have to sum over, you have to do one calculation for every single point in your training data, which is a big computation for the computer. And so stochastic gradient descent means you just choose 100 or so bits of training data, compute your loss function based on that, do your gradient descent based on that, choose another random subset, etc. So that's stochastic gradient descent, SGD, and that's usually how these things are optimized. So this optimization is non-convex, and it's an absolute miracle that it works. So you absolutely do not have kind of uniqueness of solutions, etc. And there's this term that needs to be computed every time, which is the gradient of the loss function at a particular point. So there's two complaints that you can make. The first one is, how do I compute this? But it turns out, I mean, if you think about it, you can compute it by the chain rule, and it's a whole lot of linear maps. And so it's not so difficult. But there's a very efficient way of doing that where you only have to kind of, anyway, there's a thing called backpropagation, which is an algorithm that is much loved in the machine learning community that computes this very efficiently. Another thing that you might complain is that like these are piecewise linear functions. So like, what happens if I'm bang on a point of non-differentiability? And there you say, well, I just wiggle a bit. It's an art, not a science. So if I'm at a point of non-differentiability, then you just have some algorithm that says, move a tiny little bit away from that point so I can compute a derivative. Yeah, so generally you watch it, so you'll look at it and say, what's the test and the training, what's the training and the test accuracy after every iteration? And then you can get very interesting kind of curves showing up. So one thing that happens is that you go training, like the training data accuracy goes 50, 60, 70, 80, 90%, 95%, 98%, 99%. And then your test accuracy is horrible. Okay? So that's overfitting, and you've done something wrong. Another thing that might happen is that your train and test data basically stay roughly close to each other and converge to something, and you can see it kind of tailing off, and you're like, okay, I'm going to get 90% accuracy and I can't do better. Or you might see a curve where it's like, you're doing it for weeks and it just keeps getting better. And you just think, okay, if I could run this for 2 years, then I could solve all the problems of the universe. Another thing that happens is that you kind of get brittle training. So it'll start increasing and then it'll drop down, and then it'll increase and drop down and increase and drop down and increase and drop down. And it's kind of caught in like a brittle training cycle that it never gets out of. But what you're after is, so basically you iterate this until you get some kind of meaningful model. Yeah. And there's a real art to looking at these training curves and seeing what's going on. Yeah. So next week, I think Joel will show an amazing visualization of training a neural net, and you can see situations in which it's like failing to train, for example. So it's absolutely not guaranteed that it's going to train correctly. The just observed fact is that in many problems it does train, and that's interesting. So I remember when I was in first year statistics, and there was basically a point of view which I think I'm not overstating it by saying it's a traditional statistical heuristic is that the way that you obtain generalization is by decreasing the capacity of your model. So if you think of having like a whole plot of points, 100 points, you don't try to fit a degree 100 polynomial through those points. You try to fit a line, and if it's actually given by some linear relationship, this line will be indicative of what's going on. So that's an example where you try to understand your problem by trying to fit it into a low capacity network. And the crazy thing that appears to happen in deep learning is that even in situations like there's these amazing papers where they give neural nets enough parameters that they could easily just memorize all the data. Like, there's, I don't know, some like a reasonably small training task, and they give it like 100 million parameters. So the expressivity of the network is enormous. And yet the net appears to converge to some solution which generalizes. It's remarkable. And I think that this capacity of neural nets to generalize even when their capacity is enormous, I don't think it's particularly well understood. Okay, so this is a massive one if you're trying to apply this to maths problems. So interpretation of a trained model is a big issue. So imagine that there's some problem in maths that you've really cared about and you've been working on for years, and then someone comes up and says, oh, look, Geordie, I trained a model overnight and it gets 100% accuracy on this problem. I'd be like, oh my God, that's amazing. Like, that solves my problem. And then I'd say, well, let's look at this. And the person could print me out a few like 100 by 100 real matrices and say, like, the answer is there, Geordie. You've just got to stare at these matrices. Yeah. And then I would have, like, this literally happened to me with DeepMind. So we, like, at some point, there's a particular thing called a coefficient of Q of a cardinalistic polynomial. And they trained some, and basically we expect that the coefficients are like more and more difficult. And they trained a model to predict the coefficient of Q, which was like one 5 by 13 matrix and one 13 by 3 matrix or something. And I literally printed out these matrices and tried to get some insight from them and just could not get anything. And this model was like getting essentially 100% on this problem. Yeah. So that's a big issue. And there's some methods of interrogating a trained model, but they're very unreliable in general. But I guess one of the points of the work with DeepMind is we applied a kind of very standard interpretability method to a model and got meaningful mathematics out of it. So yeah, there's a real elephant in the room, which is you've got this model and you just don't know what to do with it. Yeah. And so like, just to harp on about this point a little bit more. So in the DeepMind project, we got a model getting essentially arbitrarily good accuracy after 3 days, and then it took us 9 months to get meaningful mathematics out of it. Yeah, it's the kind of timescales. It's very useful. So this is very well explained in the Goodfellow Bengio Corville book on deep learning, which is on the website. So if you think about what we were saying in terms of kernel methods, so you start off with your Rn, and then you want to put this in some RND, and then you want to apply linear layer to this. So this is coming from kernel methods. But now I think it's very interesting to think, oh, maybe we can iterate this. So maybe there's a kernel method to R to the ND minus 1, such that each of these parameters is learned off this, is a linear learning off this. And then as you repeat back, you get to the structure of a neural net, if you fix your nonlinearity to be ReLU. And also, an important point is that there's a kind of compositionality of this. So a lot of aspects of kind of like human cognition appear to involve composition of simple functions. And that's potentially why neural nets are so good at modeling these basic human tasks. So thank you very much for listening, and you're welcome to come to the tutorial tomorrow. And otherwise, we'll continue next week, and Joel will tell us about CNNs and other neural network architectures and expressivity.